right? The meeting is now being recorded, right? So anything said from here beyond, I will try to upload the meeting, right? And in YouTube, and I will forward the link in my e-learning, right? So once again, let me welcome you. So I'm going to put up the share screen here, right? You all hearing me? I hope you all hearing me, right? Okay, so this is the lecture notes from Dr. Samouj. Of course, you know that this information here will slightly differ, right? The times that we will have classes during the short semester, the summer session is on a Wednesday from 10 to 12, as you are aware, and on a Friday from 1 to 3, right? This is the course web page. So this is Dr. Samouj web page here, right? So on this page, you will be able to access all the notes, all the problems, the text, and so on, right? So let me just see if I could pull up this text here. All right, let me pull it up here. Just give me a second. Right, this is the course web page here. Right, so you're seeing here the class notes. It could be found here, right? A table of the Laplace transform, right? The assessment for the short period is also 50% coursework and 50% final. So you'll get a Moodle, my e-learning coursework exam with 10 questions, right? I think 8 questions would be numerical response and 2 would be multiple choice. And then of course you'll have your one final exam with 50%, which is a face-to-face exam in UE. All right, so some of the references for the course would be this, the lecture notes, so Math 2230. This is our reference text here, Dawkins, differential equations, shift, and this is the text here, Finan, that we will be using with the theory, the problems and solutions, right? So here you could find past papers and previous assignment solutions, right? The videos, Dr. Samouj videos are posted on YouTube. And these are some of the recommended practice problems from the Finan text, right? And these are some additional problems here. Now, these problems are not for marks. These problems are to be done for practice, right? So it will help you to grasp the concepts and the theory so that you'll be able to perform in doing the coursework exam and the final exam, right? So the other texts, you could also use them as reference, right? So any questions so far? Okay. All right, so let me begin now by going through the material. Right, so this course is basically on the Laplace transform. The entire course is on the Laplace transform. Now, the Laplace transform is a very important thing that you normally do in engineering, especially in electrical engineering, right? Because you would need it in things like systems and transfer functions. And I think you will also need it in some of your communication courses as well, right? So these are some of the topics here, right? These are some of the headings here, the definition, integration review, examples, linearity, piecewise continuity, the inverse Laplace transform, the shifting, the scaling theorems, and so on, the Laplace transform of derivatives, solving differential equations, periodic functions, poles and zeros, and initial and final value theorems, right? So here again, you see the same web page with all the recommended text, right? Here's an additional one here. So you can take a look at that as well, right? So this is the first aspect of the course here, the definition of the Laplace transform, right? So the Laplace transform changes a function, a time variable function, to a corresponding ys, a s variable function, right? So this s variable function is basically a complex function, a frequency function, right? So you're going from time to another variable, a s variable, which is complex, right? So you see yt under the Laplace transform, small yt becomes capital Ys, right? So here we have some examples here of the application of the Laplace transform. So t changes to 1 over s squared, e to the 2t changes to 1 over s minus 1. And in a while we'll see how we do this, how this is performed by the application of the definition. So these are just a few here. Cos 5t is s over s squared plus 5 squared. Now, one very important thing you should notice when you're when your variable changing under the Laplace transform, your t variable changing to a variable in s, you notice that in all cases here you have a rational expression here basically, which is like a fraction. You understand? Something over something, right? And notice that the denominator, the power in the denominator is always higher than the power in the numerator. So you see here, the power in the numerator here is 0, so you have a constant. The power in the denominator here is 2. Here the power in the denominator is, right? The degree of this denominator here is 1 because s is to the power 1, and the degree here is 0 because it's a constant. And you see in here again, the degree in the denominator higher than the degree in the numerator. So you have s to the power 2 and you have s to the power 1 here. So that is something very important to note with the Laplace transform. It always transforms the variable t into some rational fraction basically, right? So look at the definition of the Laplace transform here, right? So L of yt is the integral between infinity and 0, e to the st minus st, and your function here yt. So you're you're integrating with respect to t then, right? Where s is a complex variable, right? And s is written in terms of sigma plus j omega. So sigma and omega here are two real values, and j here is your complex unit then, right? In integration review, so you should have some basic knowledge of integration, right? So here you're integrating between 0 and between infinity and a gt, right? And this is how it's defined, right? So you're taking the limit as r tends to infinity, and then you're changing the limit on the function here from infinity to r, and your lower limit is a, and then you're integrating your function here with respect to t. Right? So the improper integral is set to converge if the limit on the right-hand side exists and is finite. Otherwise, the improper integral is set to diverge, right? So in order for convergence, this value here must be a finite value. When you perform your integration and you take the limit, it must be a finite value, right? And if it's not, if you get infinity, it means that the improper integral would diverge, right? So let's look at some examples here. Determine if the following improper integrals converge or diverge. So you have e to the minus t between infinity and 1, e to the t between infinity and 1, right? So we are applying the definition again, right? So look at the definition. Look at the definition here. The limit as r tends to infinity. You change the upper limit to r. So basically that's what we would do here, right? The limit of r tends to infinity, upper limit is r. So between r and 1, e to the t. And when you integrate e to the t, right? What you do, you divide by the constant in front the t, and the constant in front the t is minus 1. So you have e to the minus t over minus 1, right? Limit as r tends to infinity. So you're taking t to be between r, the upper limit to be r, and the lower limit to be 1. So if you plug r into here, you'll get minus e to the minus r, which is this value here. You understand? Minus e to the minus r. And if you put 1 into this here, remember you have to minus the lower limit. So when you minus, you'll be minusing minus 1 here. So it will be plus e to the minus 1 then. So the only thing being done here is you just rearrange the terms then, right? So you put the positive value in front and the negative value behind, right? So then you take the limit here as r tends to infinity, e to the minus 1. Well, you don't have any r here, so this will remain as e to the minus 1. However, you're subtracting this limit here, e to the minus r, right? Now, if this r tends to infinity here, what will happen here, right? This could be written, right? This could be written here as 1 over e to the r, right? The lower exponents, right? So e to the minus r could be written as 1 over e to the r. And if r tends to infinity in the denominator, it means that this exponential, this is an exponential function here. So if r tends to infinity, it will blow up. So this denominator here will approach infinity. So if the denominator approach infinity, it means that the fraction will get smaller and smaller and smaller. Eventually the fraction will tend to 0. So that is how you get 0 here, right? So the value here will just be e to the minus 1, which is a finite value, right? E to the minus 1 is 1 over e, right? So that is a finite number, as you are aware. So it means that this integral will converge because you're getting a finite value, right? So let's look at the second one here now, right? So you have e to the t. So you take the limit of r approaching infinity, e to the t between r and 1. So when you integrate e to the t, you'll get e to the t. Just like e to the x is e to the x, you differentiate it or you integrate it, it doesn't change. So you have t between r and 1. So when you plug in the limits here, you'll get e to the r minus e to the 1, right? And this here, e to the r, if you have r approaching infinity, of course, this will blow up towards infinity. E to the infinity would blow up to infinity. So this infinity minus e to the 1 is infinity. So this is infinity, right? So if you have infinity and you minus a finite value, you still have infinity. So it means that this integral diverges, right? So the first one converges and this one diverges, right? So another issue to consider with the definition, right, is that S is a complex variable which may be written as this here, which we already examined earlier, right? And this is an important note here. In practice, we shall see that S is usually treated as a real constant when evaluating the integral. This can be justified by the fundamental theorem of algebra. So sometimes you could treat S as a real constant, right? And you could just perform your integration using your basic rules of integration, right? So let's look at this here. Yt is ut. So digression here, the function yt can be written as ut plus j vt, defines a complex value function when ut and vt are real valued functions, right? So let's look at an example here. So this here is like your u, and this here is your v, right? So this is a complex valued function. For example, if you take t to be 2, you put 2 here, you'll get 16, 2 to the power, 2 is 4, 4 fours are 16 minus 1, and 2 fours are 8, so you'll get 15 plus 8j. The definition, the definite integral of a complex valued function is defined as this here, right? So basically what you do, if the integral is of this complex valued function, you break up the complex valued function into two parts then, right? So you take the integral between b and a of the ut, and then you pull j on the outside, which is the complex unit, and you integrate the second part, right, which is vt between the limits b and a, right? So that is how it's defined here. So I mean, you could find the integral of this function here, right? This is a complex function, right? So you have a real and imaginary part here. So two ways you could do this, right? The first way, you could just expand this here, right? 2t plus j squared. So you use your normal rules when you're squaring a binomial. You square the first term, you multiply the first and the second term, and you double it, and then you square the second term, right? So when you do that here, what you'll get? You'll get 40 squared, 2t by j is 2tj, and then you double that, you get 40j. And then when you square j, you get minus 1, right? Because remember, the complex unit, j is the root of minus 1, right? So when you square it, you get back minus 1. And now all you do is you group the parts, right, that don't have j in it. So you have 40 squared minus 1. And then this part here with the j in it, 40j, right? And then you apply the definition, you break it up into this part here, the real part, and this imaginary part. And you take the integral using your normal integration rule. So that would be 4t cubed over 3 minus t. And then this will be j 2t squared. Sorry, this will be 4t squared over 2, right? And the 2 will divide the 4, so you'll get 2t squared. And you take the limits between 1 and 0, right? So here now, if you take, of course, 0 here wouldn't give any contribution, right? So when you're putting 0 here, you ain't getting nothing. So you have 1 here, so you get 4 over 3 minus 1, which is a third, right? And from this part here, the 0 won't give anything either. So you have 2 by 1 cube, which is 2. So that is 2 by j. So you have a third plus 2j, right? Any questions so far? Okay. Right. So this is the second way we could do it if we don't want to expand the this function here. If we don't want to square it, right? We could just use the normal rules of integration, right? You could use the chain rule here, right? So you have here, you multiply right? You have here the integral between 1 and 0, 2t plus j squared, as if it was real. So you're treating this j here as if it was a real number, and use your normal integration rules. So what you do here now, so this is a function. So what you do when you're integrating this as a function here, add 1 to the power, and you divide by that new power. So that will be 2t plus j cube over 3. And then you further divide by the differential of the inner function, which is 2t plus j. So if you differentiate this here inside, you'll get 2. So then you have to divide by 2. So if you have a 3 in the denominator here and you have a 2 in the denominator here, right? A 3 by a 2 will give you 6, right? Now you could just work backwards and check it for yourself to see if it works. So if you differentiate this here now, what you get 3 on the outside, right? To the power 2, right? So if I work backwards, I'll get 3 here, 2t plus j to the power 2, right? If I work backwards. Right? And then I had to multiply by the, right? I using the chain rule here, multiplying by the differential of this inner part here, which is 2, right? So 3 into 3, 1, 3 into 6, 2, right? And this 2 and this 2 here will cancel, so I'll get back this here, right? So that is just treating the j here, right, as if it was real, and using your normal integration rules. So now here I have the integral here of the function, right, and I'm taking it between 1 and 0. So that will be 2 plus j cubed. So I could pull the 6 on the outside here. So I have 1 over 6, 2 plus j cubed. And then I have to minus when t is 0. So that will be just minus j cubed. And here now, I cube this function here. So that will be 2 cubed using the binomial theorem, plus 3 by 2 squared j, plus 3 by 2 to the power 1 j squared, plus j cubed. And then I have to minus my j cubed. So this here will cancel, right? So what I'll get 8 here, 12j, right? And this j squared here is what? Minus 1. So that'll be minus 6, right? So this will be 2 plus 12j, right? And if you divide that by 6, you'll get 1 over 3 plus 2j, which is the same thing we got up here, right? right? So you see how you could, two ways you could basically solve this integral. Right, so the first examples here, we're looking at using the definition of the Laplace transform, right, is L of yt is the integral between infinity and 0, e to the minus st, yt dt, right? So it's defined only for these values of s for which the improper integral converges. So that is something very important you have to note, right? So you could only find the Laplace transform, right, for functions which the improper integral converges. So if it diverges, you can't find the Laplace transform, right? So that's important to know. Use the definition of Laplace transform to show that e to the 3t is 1 over s minus 3 for real s greater than 3, right? So L of e to the 3t is the integral e to the minus st, and wherever you have your function, you replace it by e to the 3t, right? So now, if you have e to a power and you have e to another power, using your normal laws of indices, right? Right, what you could do, you could just add the powers, right? So this would be minus st plus 3t, which could be written, if you take the minus sign on the outside, brackets s minus 3 of t, right? Because you'll get back your minus s here and you'll get back your plus 3 when you multiply by the negative on the outside, right? And if you apply the definition of the Laplace transform as the limit of r approaches infinity, you change the upper limit here to r e to the minus s minus 3 t dt, right? So now we're looking at this integral here between r and 0, and we want to take it as r tends to infinity. But first, right, we want to investigate this carefully. So we want to consider two cases here. We want to consider when s is 3, and we want to consider when s is not equal to 3. Now, if s is 3 here, you notice 3 minus 3 is 0, right? So you'll get e to the 0t. And anything to the power 0 is 1. So when you integrate 1 with respect to t, you'll get back t, right? And you have to take the limits here, r and 0, so you'll get r. And as r approaches infinity, this r here will approach infinity, so this here will diverge. So this here will obviously diverge then, right? So therefore, the Laplace transform, you can't find the Laplace transform, you can't apply it there in the case when s is 3. So you notice up here they said that real s had to be greater than 3, so we check in. So this is one case here showing that when it's 3, it doesn't work. Again, now from above, we see that the improper integral on the right-hand side does not converge for s equal 3. So the Laplace transform e to the 3t is not defined for s equal 3, right? So now we consider in here when s is not equal to 3, right? So here now, so when we integrate an exponential function, right, what we doing? We dividing by the constant in front of the t, right? So what is in front of the t here? Minus s minus 3. So you have to take this and divide it, e to the minus s, e to the minus, open bracket, s minus 3t. So you have to divide this here by minus s minus 3 at the bottom here, and then take the limits t equal r and t equals 0, right? So first of all, if you take the limit r here, right, you'll have the t being replaced by r. So you'll have minus e to the minus s minus 3 in bracket r over s minus 3. So of course that will be negative. So I write that on the right hand side. And then you have to subtract this here. So a minus minus, the two negatives will give you a positive, right? So I could put that term at the front, and then this t here will be replaced by 0. So anything to the power 0 is 1. So it will be 1 over s minus 3, right? So I just rearrange the term. I put the positive term in on the left and the negative one on the right. I could have write it in the reverse order, but because I find it does look more neater in this way there and easier to see and understand when the positive term is on the left, right? But if you write the positive term on the right and the negative term on the left, no problem. So you're taking the limit now as r approaches infinity. So that is 1 over s minus 3, right? This term here, no r in it, so you could pull out that term, and you're just taking minus in the limit as r tends to infinity. E to the minus s minus 3 in brackets to the power r over s minus 3, right? So you notice this here, r going to infinity here, right? This s minus 3, I could pull it on the outside, so minus 1 over s minus 3. So this is the value here we're looking at here carefully, right? Now, let's recall that s is a complex variable, right? It could be written as sigma plus j omega, right? If the real of s is sigma, is the real part of the complex constant, we now wish to show that this here is either 0 or it diverges when the real part is greater than 3, and when it's less than 3, it diverges. Now we already consider the case when it equals to 3, right? So let's look at this here. So you have e to the minus s minus 3 in bracket r. You're taking the limit as r approaches infinity, right? You're replacing your s here by sigma plus j omega minus 3, right? And you have your omega minus 3. Sorry, your sigma minus 3. You group the real part together, sigma minus 3, and you put the complex part here separately, plus j omega. And then you break up this exponential into e to the minus sigma minus 3r by e to the minus j omega r, right? So this is negative because you have a negative outside. So the both terms will be negative, right? Now this part here, recall Euler's formula, right? Look at Euler's formula here. E to the j theta is cos theta plus j sine theta, right? So look at this part here, the omega r, right? So you have your j. So wherever you have theta, you replace it by omega r. So that will, you could evaluate that using Euler's formula to be cos omega r. And since you have a negative here, it will be negative j sine omega r. Right? Because if you have a negative j theta, this will be cos theta minus j sine theta. So when you have negative here, the formula slightly changes, the sign between changes from plus to minus. Hence the reason why we have this negative here, right? And now you have e to the minus sigma minus 3r. So you'll have to multiply this by the cos omega r, and then you're subtracting j, the limit of that, e to the minus r minus 3, e to the minus sigma minus 3r by sine omega r. Right, so here now you have a product here, and you have a product here, and you have the difference between these two terms here. So you're going to take the limit of this part of the product, and then the limit of this part, and then you could do the same with the other value, the limit of this part, and the limit of the sine part. So that is what is being done here, right? So of course here, if this here approaches infinity, right? This could be written as 1 over e to the r minus 3. I keep saying r, but this here, sorry, this is sigma. Eh? So this is sigma right? Because you put it in the denominator, so which means if r approaches infinity here, you have 1 over infinity. So this will approach 0, so this term will be 0, right? And of course here, if r approaches infinity here, right? This will also be in 0, right? And just like how this term are now evaluated here, the same thing here with this here, so this could be 0. Sorry, if this is 0, 0 multiplied by anything here is 0, right? This will not approach 0. But what you'll get here, this will be 0, right? Right? If cos approaches infinity here, you'll have an oscillation, but 0 by anything, right? 0 by anything is 0. And similarly here, if r approaches infinity here, you have an oscillation taking place here. But this term here will be 0. So 0 by anything here is also 0. So you'll end up with 0 minus 0, which is 0. Right? So that would be the case when sigma is greater than 3. Because if sigma is greater than 3 here, you'll have like 4 take away 3 is 1, 5 take away 3 is 2, 6 take away 3 is 3. So you'll end up with a negative whatever. Once this value in here, this value for sigma, right? This value for sigma is greater than 3. Here will always be negative, right? But if this here is less than 3, if you like, if you have 2, right? So 2 minus 3 is what? Minus 1, right? And minus 1 is plus 1, right? 0 minus 3 is minus 3. So anything less than 3, you'll end up with a negative, which will give you a positive. So therefore, you'll have divergence. This will end up blowing up to infinity, right? So it's very important to say that the real S, omega has to be greater than 3 in order for you to get 0, because these terms here on the outside would be 0. It doesn't matter what the cos and the sine works out to be, but 0 by that will always be 0. right? Right, so here now, so any questions on that? Any? Just pause for a minute to see. Right. Right. So this here is a example, a diagram here showing the convergence, right? The convergence of the e to the minus sigma minus 3 by r cos omega r, right? Right. So this is a sinusoidal, right? So a sinusoidal is a kind of a sine wave, right? And if you notice here, you notice that this sinusoidal is kind of enveloped, right? Right, so it's enveloped, it contains between this kind of values here you're seeing with the dotted line here and the sinusoidal as it moves, right? It gets smaller and smaller, right? So we say that it's damped, right? So the fact that it's getting smaller and smaller as it moves along means that it's convergent, right? So you see convergent for sigma greater than 3, right? And this one here, watch out what happened here. So this one showing divergence. So it's not damped, but you see oscillation taking place, right? So what happening here is it's starting to open up wider and wider as it goes along, right? So this here would be the graph for when S, the real S, sigma is less than 3, right? So this one here is not damped. So we could summarize all that was done here so far now. We could say that the Laplace transform at e to the 3t is equal to 1 over s minus 3 minus 1 over s minus 3. The limit of r tends to infinity, e to the minus s minus 3 in bracket by r, and the limit e to the minus open bracket s minus 3 by r is equal to the limit of e to the minus open bracket sigma minus 3r cos omega r minus j, the limit of e to the power minus sigma minus 3 in bracket by r sine omega r, and is equal to 0 when the real s is greater than 3 and it diverges when the real s is less than 3. Right, so that is the summary of the Laplace transform. So the Laplace transform here is only defined when the real s is greater than 3, and it diverges otherwise. When it's less than or equal to 3, diverges. We already looked at the case where it was equal to 3. So hence, when it's greater than 3, when the real s is greater than 3, right, which is sigma greater than 3, you will get 1 over s minus 0, which is just 1 over s. It diverges for less than 3, and it also diverges when s is equal to 3. Right. It may also be shown that the Laplace transform e to the 2t diverges when the real s is 3. Hence, the Laplace transform e to the 3t is equal to 1 over s minus 3 only when the real s is greater than 3, right? So this is supposed to be so you could try this here as an exercise. Definition: the region of convergence, ROC, of the Laplace transform. So LYT, integral between e to the minus s ty t dt, is the range of values of s for which the improper integral on the right-hand side of 8 converges. Right, so we have it drawn here. So the same function here, e to the 3t is 1 over s minus 3, is the real s is greater than 3. The region of convergence may be illustrated on the complex plane. So here you have your real axis and you have your imaginary axis, right? And you have your real s is equal to 3. This is this line here. So that is like your x-axis basically, right? And why you think we have a dotted line here and not a solid line? We have a dotted line here because when s is 3, you have divergence. So the only time you have convergence is when s is greater than 3, right? So just like when you're doing inequalities, if it doesn't include the endpoint, you will have a dotted line or an open circle, as the case may be, right? So you have a dotted line here, meaning that on this line here, on s equal to 3, there's no convergence. Convergence is only to the right. You understand? So everything to the right of this line, this vertical line, you have convergence. And you don't have convergence otherwise, right? So that is how it's represented on the diagram. Right. So let me pause a little bit here again and ask if anybody have any questions before I move on. Right, so I see some people came in a little late in the session, right? So what would happen is they would have to look at the recording, and they would get some, they would be able to look back and see what was done prior to them coming into the session, right? So they're just pausing for a few moments. Okay, I just want to say one more time that that we have sessions on a Wednesday from 10 to 12 and on a Friday from 1 to 3, right? So normally, as we are starting today, I will go through the lecture notes, and then At some point, maybe after the first 2 sessions, I will start going through doing a tutorial. So intermittently during the sessions, I will go through questions and which we will normally call a tutorial, right? So as we go through the topics, you'll get practice, right? And I just want to say one more time, I have to reiterate that you have one coursework exam, which is worth 50%, right? For the people who came in late, and your final exam is 50%. The final exam is a face-to-face exam, right? You're coming out and you're doing the final exam on campus, and the coursework exam is an exam that you're doing my e-learning, right? So you'll get like about 10 questions. About 8 of the questions will be a numerical response, and 2 of the questions would be multiple choice, right? So I will let you know when the coursework exam will be scheduled. I'll let you know in advance, and I'll give you information regarding up to where you'll be tested, right? Okay. So let me just go back to the and the course web page. You could access all the information, the notes and so on. And you could also look at the questions, the suggested questions to practice. But those questions are only for practice, for you to understand the concept, not for marks. Right. So now we could make a proposition here now, right? So we have here, if L of e to the 3t is 1 over s minus 3 and real s is greater than 3, you could generalize this statement here, right? So if you say, all right, W is a complex number, and W could be written as A plus JB, right? So this is a complex number here, or a complex constant, right? So if you replace 3 here by W, right? You follow the basic rules. L equal e to the WT is really 1 over s minus W, right? And it means that this, based on what we just derived here, real s must be greater than real W, right? Because you replace the 3 with the W. So you have a corollary here now. If A is a real constant, then the Laplace e to the AT is 1 over s minus A, when the real s is greater than A. Let W be equal to 0, right? So if W is 0 here, then you're replacing W with 0. So you get e to the 0 is 1 over s minus 0, right? And what is e to the 0? E to the 0 is 1. So you'll end up getting the Laplace of 1 is 1 over s, right? And when the real s is greater than 0, remember your W is 0. Right, so we have another proposition here. T to the n is n factorial over s to the n plus 1, where the real s is greater than 0, right? So let's look at this proposition here, T to the n. Sketch of this can be seen on page 72 of Math 2230 course notes. So you'll find that in the web, on the web page. Right, so we could use induction here. So the Laplace of 1 is 1 over s when real s is greater than 0. So how you could express 1? You could express 1 as t to the 0, because t to the 0 is equal, anything to the 0 is 1. So we have a proposition here. So what we have to do first and foremost here, right, to test this result here, we take t to the n to be 1, and t to the n could only be 1 when n is 0. So which means on the right hand side here, you will get 0 factorial over s to the 0 plus 1. Look at here, 0 factorial over s to the 0 plus 1, which is 0 factorial over s. And 0 factorial is 1. 0 factorial is defined to be 1 for real s greater than 0. Right? So which means that this statement here will be true for n equals 0. So now we're looking at the inductive step now. So you know with mathematical induction, first of all, you just show that it holds for the first case. And in the first case here is when n is equal to 0. Right? So let's use the definition now of the Laplace transform on t to the n. So t to the n is really the integral between 0 and infinity, e to the minus st. Right? And you replace your function here by t to the n. Right? Which is the limit as r tends to infinity. Right? Between r and the limits, the limits of the integral now, you change the upper limit to r, and you take the limit as r approaches infinity, and the lower limit is 0, right? And then you treat here as an integration by parts, right? So you're calling this v, and you're calling this du, right? So you know, anytime you're integrating by parts, right, you have v du is equal to uv minus the integral of u dv. Right, so that is what we're doing here. So this here is your v du. So you need to get you need to get u from this, and you need to get dv from this. So if v is t to the n, right, then dv will be what? Then you differentiate this with respect to t, that will be n t to the n minus 1. Right? And if this is, du is this part here, then you have to integrate that. When you integrate that, what you'll get e to the minus st. You're integrating this with respect to t. So you have to divide this by the constant in front of t, which is minus s. Right? So now you could break up the integral now, right? Which is v du, taking the limit as r approaches infinity between r and 0, e to the minus st, t to the n is the limit as r approaches infinity, right? uv, look at u and your v here. So when you combine these, you get minus t to the n, e to the minus st over s. So the minus e to the minus st, t to the n over s, look at here. And you're evaluating that between r and 0. And then you're adding, you're subtracting, right, u dv. So you subtract, this is your u and your dv here. but this have a negative in it. So if you're subtracting, the double negatives will give you a positive. So you could pull out the n and the s here. So you'll have n over s. The limit as r tends to infinity, the integral between r and 0, e to the minus st, t to the n minus 1 dt, right? So this part here, when you put in r here, right? Of course, when you put in, for t here, you put in r, you'll get e to the minus s r, right? And you could write that as 1 over e to the s r in the denominator, as I showed you earlier on. So that means your denominator will blow up, right, exponentially. So as that r approaches infinity, when your denominator getting bigger and bigger, your fraction getting smaller and smaller. So eventually it will approach 0, right? So what you'll have here, basically here, let me show you. Why it approaches 0. This could be written as minus t to the n over e to the st, right? So you could put this part in the denominator, and then the s here, right? And you could pull the negative outside, right? Now remember, you're replacing this t here by r, right? And you're replacing the t here by r, but which limit? Which one will approach the limit faster? The numerator or the denominator? Obviously the denominator, because the denominator have exponential in it. So this will approach infinity a lot faster than this up here. So that means this will approach 0, right? So this term here, of course, when you put in t to be 0, the top part here will be 0. So that will be 0 over 1. So that will be 0. So the top part, the 0 part here won't give any contribution. The r, when you substitute the r here, this will become 0. Because of the fact that it could be written as this here, with the exponential in the bottom and the exponential approaching infinity a lot faster, right? Because the exponential function blows up faster than a normal function. So that means that the front here will be 0. And then you have n over s, the limit at r approaching infinity of this here, this term here, right? Now, this is essentially the definition, right? T to the n, e to the minus st, right? Look at here. Could be written as the limit of r approaching infinity, the integral between r and 0, e to the s minus st by t to the n dt, right? So if you replace the t here by t minus 1, therefore that will be L t to the n minus 1. So this here is basically the same definition here. Just the t is now, instead of t being to the power n, is t to the power n minus 1. So therefore we could replace that as the Laplace at t to the n minus 1. And you have n over s in the front, right? So t to the n is n over s, L to the Laplace transform at t to the n minus 1, right? And now you could continue substituting for t to the n minus 1. Now notice here, the Laplace transform at t to the n minus 1 could be written as n over s, the Laplace transform, at 1 power less, t to the n minus 1, right? So if you use that same principle here, it means that the Laplace transform at t to the n minus 1 could be written as the Laplace transform are 1 power less than, which is t to the n minus 2, right? So you see here, look at here. But this time now you'll have to multiply, right? So you multiply by the power n, right? And you minus 1 from the power and you divide by s. So the Laplace transform at t to the n will be n t to the n over s t to the n minus 1. So the Laplace transform at this could be, you multiply by the power n minus 1 over s, the Laplace transform at t to the n minus 2, right? And then you do the same thing with this here now, right? So that would be n over s, n minus 1 over s. And then you have n minus 2 over s, right? By the Laplace transform at t to the. So I just put in an extra step here, n minus 3. Right? And you have n by n minus 1 by n minus 2. What you think the next factor will be? Not n minus 3 and n minus 1, so on. So that's showing you the top will be n factorial. Now n factorial is go all the way down to what? n minus 1, n minus 2 by 2. By 2 by 1, right? So every time you multiply by a value here, then the n factorial, you have to keep dividing by s. Right? So you see what this pattern here, n over s, n over n minus 1 over s, and so on. You see the 2 over s here but I didn't write the last one, because if the power here is 2, right? If t to the power 2 could be written as all of this here by the Laplace at t to the power 1, right? And then the t to the power 1 can be written as t to the power 0. We already know what t to the power 0 is, right? So what should happen here? You have n by n minus 1 all the way down to 2 by 1 over s by s by s by s. So this will be, if this going all the way down to 1, so this is n factorial, and this will be s to the power n, because this s being multiplied n times, because this is n times up to 1 here. And then the 0 here is an extra 1 over s, right? So that will be n factorial to the over s to the power n by 1 over s, which is n factorial over s to the power n plus 1, right? So you have the next value is L Laplace transform at t to the 0. Right, I didn't have down to the 0 here, but you could define the Laplace transform at t to the 0, which we did originally, and that was 1 over s, right? So this is true, the Laplace transform at t to the n is equal to the n factorial over s to the n plus 1 when the real of s is greater than 0. Right? So now here, use this here to show L1 is 1 over s, right? Which we already did, right? That will be t to the power 0, which is 0 factorial over s to the 0 plus 1. So we already showed this. This is t to the 1 here now, right? So if you put 1 here, you'll get 1 factorial over s to the 1 plus 1 is 2. 1 factorial is 1, and s to the 1 plus 1 is s to the power 2. And 2 now, so you put 2 here, 2 factorial is 2 over s to the 2 plus 1 is 3. Right, so you have 3 results here. The Laplace transform are 1 t squared. And you could continue the process and find any power t. Right? Right, so let's look at the linear property of the definite integral and how it can be stated. Right, so you have an integral between b and a, right? You have a constant by one function plus a constant by another function. You could break it up into the integral of one function plus the integral of the other function, right? And you have the two constants on the outside of the integral. Right, so this property allows the definite integral to be broken into sums. Right? The Laplace transform is defined using definite integrals. So in other words, when you're dealing with when you're dealing with Laplace transform, you don't have indefinite integral. You always have limits, right? So when you have indefinite integrals, you wouldn't have limits. So therefore, when you integrate, you will get a constant. But with the Laplace transform, the definition is always with definite integrals. So you always have limits to apply into the integration, right? So you have the Laplace transform here once again of yt. By definition is the integral between infinity and 0, e to the minus styt dt is equal to the limit at r approaching infinity, and you change the upper limit infinity to r. The lower limit remains at 0, and you take the integration of e to the minus st by the function yt. Right, so this implies the linearity property of the Laplace transform, where you could break up the combination of two functions under integration into separate integrals, right? Okay. So let's state another proposition. So by definition, the Laplace transform of a function y, right, a function in time variable, so we call in this function y1t, right, would be capital Y1s. Because remember, when you take the Laplace transform, you go from t to s. You go from common y to capital Y, right? So you go from time to frequency, and your frequency here is complex, right? So you have L is y2t, is capital Y 2s. And in both cases here, you have the real S being greater than a value, A1, and your real S being greater than another value here, A2. And these values, A1 and A2, define real constants. Then any constant C1 and C2, which could possibly be complex, we have the same thing happening here, right? We have L as C1 Y1T plus C2 Y2T is C1 YS Y1S plus C2 Y2S. And you have the real S would be the maximum of the two constants, the real constant. Right, so we could use the linearity property here, the Laplace transform at 2t plus 3 e to the 2t. So that will be 2. This is your constant here. You could pull it out on the outside. So you're taking the Laplace transform at t. This is your constant. You could pull it on the outside. You could take the Laplace transform at e to the 2t. So this will be, we know that the Laplace transform at t to the power 1 is what? 1 factorial over s to the power 2, right? So this is 1 over s squared. And we know that this here is 1 over s minus 2, right? But you have a 2 here to multiply, and you have a 3 here to multiply, right? So you'll end up with 2 over s squared plus 3 over s minus 2, right? And your two real constants here are 2 and 3, right? So when s, the real s is greater than 2, because the maximum of 0 and 2 is 2. So therefore the Laplace transform will be defined for real s being greater than 2, the maximum of the two of them, because 2 is greater than 0. Right. We already spoke about this here, the Euler formula. E to the jwt is cos wt plus j e to the j omega t, sorry, is cos omega t plus j sine omega t. And e to the minus j omega t is cos omega t minus j sine omega t, right? Now, a simple little thing here, that why this is defined like this here? Why the negative is why I didn't have a negative in front of the cos here, right? Because what would happen here if I use this first definition here, right? And now I switch to minus. Then what will happen? This will be minus, and this will be minus. Remember, cos is an even function. So cos of x is equal to cos of minus x. So it doesn't matter if you take the cos of if your argument is positive, your argument is negative, it will be the same thing. So therefore, this here, cos of negative omega t is the same as cos of omega t, right? And your sine function is odd, right? Cos of x equal that is why this here doesn't change, because it's minus omega t, but minus omega t is the same as omega t. But if you have sine minus x, because sine is an odd function, and this is defined as negative sine x. right? So if you put minus omega t in here, that will be the same as minus j sine omega t. Hence the reason why we get this for your definition here of e to the minus j omega t, right? Because cos is odd, sorry, cos is even and sine is odd, right? Now, if we add these two, e to the j omega t plus e to the minus j omega t, then we go have to add the right hand side. So you go have to add this and this. So you'll get 2 cos omega t, and then you go have to add a plus. These two will cancel because one is positive, one is negative. So you just get 2 cos omega t, right? And then if you divide by 2 here, you'll get cos omega t is e to the j omega t plus e to the minus j omega t divided by 2. And e to the wt is 1 over s minus w from before, when real s is greater than real w, right? So this here, if we put in e to the j omega t, right? All you have to do is replace the w here by j omega. So that will be 1 over s minus j omega. And in this case here, the real s will be greater than 0, right? So you replace your w here by 0. As this here is real, the real part of j omega is 0. Similarly, e to the minus j omega t, right? So replacing the w here by minus j omega. So a minus plus, so s plus j omega. And again, the real part here is greater than 0. Since real of j omega is 0. So the Laplace transform of cos omega t would be the Laplace transform of a half e to the j omega t plus e to the minus j omega t. And if you apply the linearity property, this will be a half the Laplace transform of e to the j omega t plus the Laplace transform of e to the minus j omega t. And this part here was already evaluated to be 1 over s minus j omega, right? From the first part here, and this one was from the second part, 1 over s plus j omega. And then you just take the LCM here. So what the LCM here will be these two. So you'll have to multiply this side here by s plus j omega, and you gotta multiply the 1 here by s minus j omega. And the j omegas will cancel, and you'll get 2s, right? And if you notice this here, you'll get s squared. The middle terms will cancel. So this will be the difference at here, 2 squares, right? So when you square s, you'll get s squared, and when you square this here, minus j omega by j omega, you'll get minus j squared by omega squared. And j squared is minus 1, right? Minus j squared is plus 1. So you'll get plus 1 by omega squared. So you get s squared plus omega squared here in the denominator. And in the numerator, you have 2s, and the 2 will cancel. So you'll end up with s over s squared plus omega squared, right? So remember, I tell you, anytime you do perform the Laplace transform, right, you always end up with a rational fraction where the power in the denominator is always higher than that in the numerator, right? So it's a proper rational fraction basically, right? And S is greater than, the real S is greater than 0, right? So summarizing the Laplace transform of cos omega t, you end up getting S over S squared plus omega squared, where the real S is greater than 0. Right. Let omega be a real constant. Use the identity sine omega t is equal to 1 over 2j in brackets e to the j omega t minus e to the minus j omega t, to show that the Laplace transform of sine omega t is equal to omega over S squared plus omega squared for the when the real S is greater than 0. Right? So you could take the linearity property on the right hand side here, evaluate this, just like how we did up here. So go through all these steps, find the LCM, and then you should end up with some kind of cancellation, and you should be able to get this here as a result, right? And then you could also do it with the cosh and the sinh, right? So you're using the definition of the Laplace transform on this one, the cosh and the sinh as well, to get these results here. Right. Any questions so far? Right. No questions? All right. Right. So let me just reiterate some of the key things we dealt with in terms of the Laplace transform, right? So this is a function here, right? Right? This is a function here. Now this is function is defined differently for different regions. You understand? So you have yt is 0 between 0 and t, sorry, between 0 and 1, inclusive of 0, right? Is defined to be t between 1 and 2, inclusive of 1. And it's defined to be 0 greater or equal to 2. Right? So this graph here showing a sketch of that function here. So you see, it's 0 here between 0 and 1. So you see the you have a horizontal line on the x-axis here because it's 0, and you have an open circle here at 1 because it doesn't include 1. Right? Now from 1 to 2, the function is defined to be t. So this is your t-axis here, right? Right? Your t-axis is like your y-axis, right? Sorry, your t-axis is your x-axis, right? Your t-axis is your x-axis. So your t-axis is like your x-axis, and this is your y-t here, right? So the function is defined to be t between 1 and 2, but it includes 1. So you have a bold circle at 1 and then you draw a line, right? So this is basically the function y is equal to t, right? So this here is a straight line, right? With your gradient being 1. You see your gradient is 1 here. So your rise here your run is 1 and your rise is 1, right? So you have an open circle here because it's not defined at t equal 2. So you have a open circle here. Now from t equal 2 and beyond, the function is 0. So you have a bold circle at the t-axis here all the way moving to infinity. Now, what do we call a function of this form? We call this a piecewise function, right? So anytime you have a function defined for differently for different intervals, we call it a piecewise function. Now, so that is another concept with the Laplace transform. So the Laplace transform only works when functions when they converge, right? For convergent functions. So it only defined for when at values for which our function converge, and the other concept is the function must be piecewise continuous. So this is a piecewise function and it continuous because it continuous here. It continuous for every value less than 1, right? Because you see that there are no breaks here. It continuous between 1 and 2, right? And it continues from 2 and beyond, right? So this defines a function, a piecewise function that is continuous. So once a function piecewise continuous and it converges, right? Then you could perform a Laplace transform on it, right? Right. So look at another one here, right? So this one between 1 and 2, right? Look at the function here. It's defined to be t. So the gradient here is 1, right? You see a bold circle by 1, an open circle by 2. But from 2, it also continuous again because you have a bold circle here and it defined to be t squared between 2 and 3, right? And then from 3 to 4, it defined to be inclusive of 3 and 4, it defined to be t 12 minus t. So here the gradient is minus 1, right? So again, this is a piecewise function, right? And it continues in the interval from 1 to 4. Look at it written here. So it means that that function, right, could undergo a Laplace transform once the function converges for certain values, right? Another thing about the Laplace transform, they say like the function must be of exponential order, right? So let me just so this is my whiteboard here. So if I have a constant c, right? So I defining 3 constants here, c, m, and t. M is greater than 0, t is greater than 0. You have the size of this function here, f of t. is less than or equal to M E So yeah, basically here you have two functions. You have this function here under the absolute value, right? And then you have this function here, e to the ct, right? So in other words, this function here bounded by this function here on the right, because it's less than or equal to, right? So what will happen as t approaches infinity? Right? So both functions will approach their limit, right? So the functions will approach their limit. So, but which function go approach the limit faster? From what we learned earlier on in what we did. Of course, the exponential function will approach the limit a lot faster. So which means that the limit of t approaching infinity, ft over e to the ct will be 0. So the quotient of ft over e to the ct will be 0 as t approaches infinity, because this function here at the bottom will approach the limit of a lot faster than this function because it's exponential. So which means the limit here will be 0 of the quotient of the two functions. And that is the concept behind a function being of exponential order, right? So the function is of exponential order c, right? So functions that are of exponential order could undergo a Laplace transform, right? Functions that are of exponential order. So the exponential order here is the constant c here in the power of e here. The variable is t, right? And you have two other constants, m and capital T, right? And they say here that t must be greater than capital T. So for all values here, because it's a function of time, all the small t values must be greater than this constant here, this capital T. And the function is of exponential order. And if you notice, when we was doing the Laplace transform and we taking the limit as r approaching infinity, and some of the values, I was taking the e in the numerator and I putting it underneath. It was the same idea as this here, right? So those functions are functions of exponential order, whatever the constant in front of the t is. In this case here, the general case here, we call it the constant c. So functions that are of exponential order could undergo a Laplace transform, as well as functions that are piecewise continuous. So once the function is of exponential order, it means that the function will be able to converge, otherwise it would diverge, right? So basically that is the whole idea behind the Laplace transform, the concept of the Laplace transform. So we were able to go through some of the basic stuff involving the Laplace transform. So the web page is there in for the time being, right? You could go up and access the material on the web page, Dr. Ramsamu's web page, right? Right, the information was given at the beginning here. Look at here, right? Google Sites, site google.com/site ECNG Math 1016. So you could find all the material there. So if you don't have any questions, we could end there, and we'll continue again on Friday, right? So thanks for attending and being attentive, and I'll see you again on Friday. Take care.
Excuse sir,
Yeah.
you hear me?
Yeah.
I got a job for the holidays for the summer, right? And the class times fallen within my working hours. I was hoping that if I could just listen to the recordings, and then I could just write the exams, and I could attempt to join the live classes whenever I could.
Yeah, no problem. Once is what is the policy with your with your faculty or your department? They're mandating that you attend classes?
I don't know, sir.
Right. Well, it's okay by me. I have no problem with it. Just make sure and do your work, right? Because the videos and them will be posted in YouTube, right? So once you do your work, is no problem with me. But I don't know what the department mandates, right? So maybe you'll have to find out that.
Okay, thanks, sir.
Right? Anything else?
No, that is it. I understand everything. I like how your teaching style is. You break down everything real simple.
All right then. Well, I hope I could. I noticed that people not really asking questions. People not they writing little things in the chat, and my style is not really to be teaching, and I feeling like I'm talking to myself. Then I always like interaction, you know. But I know sometimes students is be kind of shy to ask, but feel free to ask, right? Because we're here to learn, right?
Yes, sir. The reason why nobody asks anything is because you break it up real simple and you're teaching good too.
All right then. Well, thanks. So we'll see you again on Friday, right?
All right, sir. I'll
Right,
try to
take
make
care.
it.
Right. Okay. Bye.
Bye, sir.
Right. Anybody else want to ask anything?
Yes, sir.
Yeah.
Question. I'm a student, I'm a Barbadian student. So in terms of the face-to-face final exam, could any preparations be made for me to sit the exam at KFL or something like that?
Right. Well, I'll have to follow up that with the department, right? So what is your full name? Let me write down your name here. Right.
Brandon Arundel.
A senior name, you know, by a senior surname. Brandon, Brandon, and spell the surname for me.
You saying it now, sir?
Oh, right. Rrendll. Right. Barbadian student, right?
Yes, please.
Right. So this first time you're doing the course?
Pardon me?
Is this the first time you're doing the course?
Yes, please, sir.
Oh, so, but I know they said that this course was for remedial, people who repeated.
Oh, yes, sir. I am doing over the course. I did the course last semester. I was in Trinidad last semester.
Oh, and you did the final exam in Trinidad, right?
Yes, please.
All right, but when you register, you didn't find out and they didn't tell you that the final exam was to be written in Trinidad, face to face?
You mean for this summer course?
Yeah.
No, sir.
They didn't tell you that, and you didn't because
I only got the email to register this morning, so I actually have to go and register right now.
Oh, yeah, well, who you're dealing with in terms of the department? Who is the personnel in the department you're dealing with?
What do you mean, sir, in terms of my academic advising?
Yeah, who you're communicating with in administration, in terms of, it could be an academic advisor, it could be somebody in admin.
I was speaking to mainly Miss Clement and my academic advisor, Marcus George.
Yeah. Yeah, because maybe you'll have to communicate with Miss Clement, tell her your situation, and I will follow up on it and see what is the verdict, because I don't know how they will arrange. I don't know if it will be possible. You wouldn't be able to come back here maybe sometime in late July to do it, just to do the exam.
I'm not sure, sir, but the reason I asked is because I had exams such as 10-11 before, which I did in Barbados at KFL, which the paper was sent over, and I had an invigilator and stuff at UWI KFL.
All right, well, something like that, some kind of arrangement like that would have to be made. So I'll communicate with Ms. Clement. I will follow up on it, right? And I will follow up on the lead lecturer too then, Dr. Ramsamuj, about it as well, right? And
okay.
I'll see, because I am not the person to make the call. You understand? I just teaching the course, and anybody else, the people in administration in the department, the lead lecturer, they will have to decide on how they're going about it. But if you say that they made a concession for you at some point in time for you to do an exam, they sent across the paper, and they had people to supervise and so on, then I think it could happen, you know?
Yes, sir. At that point, it was me and 2 other agents, but right now it would just be me. But I hope that, you know, the same preparations could be made.
Yeah, so if that had to happen, it had to be done the same day and time. So while you doing the exam, everybody in Trinidad had to be doing it too.
That's expected, sir. Yeah, that's expected.
And then when you finish do the paper got to be sent to Trinidad to mark.
Yeah.
So you know, the contact in terms of getting the paper across there in time and bringing it back to Trinidad on time, in order for you to be graded and for you to get your marks within a reasonable time frame. All these the logistics side had to be worked out in order for things to go smooth. Right? So I will communicate, and you could communicate and follow up on it. Don't take it for granted and find out, right?
Okay, thank you.
Okay then. All right. Anybody else? Okay then. Okay, so we'll end here.